myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to start microwave cavities. Already we have discussed about the waveguide, that is rectangular and circular waveguide, in the previous lectures of mine, and today we are going to start the microwave cavity. Basically, the microwave cavities are advancement of our waveguide which we have studied earlier. So, a cavity resonator is a metallic enclosure that confines the electromagnetic energy. The stored electric and magnetic energy inside the cavity determines its equivalent inductance and capacitance. So, basically what is this? Microwave cavity is a metallic enclosure that can store the energy inside it, and that energy is stored in the form of electric energy or the magnetic energy. Already we know that what is the equation of energy stored in the terms of electric field and in the terms of magnetic field. The energy dissipated by the finite conductivity of the cavity walls determine its equivalent resistance. So, when the stored energy inside the cavity determines its inductance and the capacitance, the energy dissipated determine its resistance. So, the most commonly microwave cavities are rectangular cavity resonator, circular cavity resonator and resonant cavity resonator. The rectangular cavity resonator can be made from the rectangular waveguide. Circular cavity resonator from the circular waveguide, and the third one is the resonant cavity resonator, about which we will study in the microwave sources in detail. A resonant cavity has a finite number of resonant mode, and each mode determine a definite resonant frequency. When the frequency of an impressed signal, that is the signal which is entering inside the cavity, is equal to the resonant frequency, the maximum amplitude of the standing wave occurs and the peak energy stored in the electric and magnetic fields are equal. So, what we are getting from this line is that when the frequency which is entering inside a cavity is equal to the resonant frequency of a cavity, about that which we have already calculated and already known to us. In that case, the maximum amplitude of the standing wave occur and the peak energy stored in the form of electric and magnetic fields are equal in that case. And the same as in the rectangular waveguide and the circular waveguide, the mode having the lowest resonant frequency is called the dominant mode, and the same definition is applicable for the rectangular waveguide and the circular waveguide, about which we have already discussed in the previous lectures. Now comes the rectangular cavity resonator. So, this is a rectangular cavity resonant. So, before going to a detail into the rectangular cavity resonator, first of all we are able to see that what is the basic difference between the rectangular waveguide and a rectangular cavity resonator. In the rectangular waveguide, this dimension is of infinite length, but in the case of a cavity, that is rectangular cavity resonator, it has got a finite value. So, what we are able to see that in the case of a waveguide, the two ends are open, but in the case of a cavity, this end is closed, this end is closed and only this end is open. So, this is the basic difference in the construction of rectangular waveguide and the rectangular cavity resonator. The electromagnetic field inside the cavity, same as the rectangular waveguide, is to satisfy the Maxwell equation and the boundary conditions, that the electric field tangential to and the electric field normal to the wall must vanish. This is the boundary condition which this cavity has to satisfy, and apart from this it has to satisfy the Maxwell equation, all the 4 Maxwell equations. Now, the wave equation in a rectangular resonator should satisfy the boundary condition of a zero tangential electric field at the 4 walls, and in that case the harmonic function in Z satisfy this condition at the remaining 2 end walls. And when we solve it, what the function we are getting? The magnetic field expression is this: Hz is equal to H naught Z cos m pi x by A cos n pi y by B sin p pi z by D. So, already we have studied about that in the waveguide section, that this is the maximum amplitude of the magnetic field, and this m values varies from 0 to 1, 2, 3 continues, and it is the number of half wave periodicity in the x direction, same as have in the rectangular waveguide. A is the dimension in the x direction, you are able to see this, the A is the dimension. Now comes the cos n pi by B, and value same as m, varies from 0, 1, 2, 3, 4, 5 and so on, and it represent the number of half wave periodicity in the y direction and the dimension of a wave of a cavity in the y direction, this one. And in the case of a rectangular waveguide, what is the difference? Rectangular waveguide Z direction is of infinite, and we assume that the wave is propagating in that direction, and in that direction we are used to keep e to the power plus minus gamma z in the case of rectangular waveguide. But here the Z direction is also bounded, so this expression can't be applicable, and here sin p pi z upon d for the Z direction, and p is equal to 0, 1, 2, 3 represent the number of half wave periodicity in the Z direction, and d is the dimension in the Z direction, because d is also fixed in this case. Now, similarly, the expression of the electric field for the rectangular resonant cavity, Ez equal to E naught Z sin m pi x upon A sin n pi y upon B cos p pi z upon D. The values are almost same, m periodicity in the x, dimension is in x, periodicity in y, dimension in y, periodicity in z, dimension in z. So, now the separation equation for both T and TM mode in the case of a rectangular cavity resonator is same, and that is equal to m pi by A whole square, n pi by B whole square, p pi b d whole square. And as we know that this k square is equal to omega square mu epsilon, and if we want, this will basically represent our cutoff wave number, and if we want to have the value of resonant frequency from this expression, so this omega we know, this is equal to 2 pi f whole square mu epsilon, and when we solve it, we get the value of resonant frequency, and that is equal to this one. If you want to solve, this is very simple problem. K value is already known to you. This is equal to this one, 2 pi f c whole square mu epsilon, and this is the k one. And when we say now we want the f c, so this will be 2 pi 1 by 2 pi and this will be k square, and this will be definitely k, and the k will be under root of this. So, this is 1, this here, and pi we take as the common, and that will get cancelled here, and we will get this expression as the resonant frequency for the T and Tm mode, both of the rectangular cavity resonator. And now comes the turn of the dominant mode. In the case, in this rectangular cavity resonator, the dominant mode is the TE101, and this dominant mode will come when A, dimension of A is greater than B, and dimension of D is also greater than B. So, when we see this figure, it should be applicable. You are able to see that A here is greater than B and D is also greater than B. So, this condition has to be applied if we are saying that this is the dominant mode. Now comes the turn of the where to excite the cavity. So, a straight probe, wire probe inserted at the position of maximum electric intensity is used to excite a desired mode. So, if we want to excite a particular desired mode which we want, so we have to insert a straight wire probe at the point where we have a maximum electric intensity, and the loop coupling placed at the position of maximum magnetic intensity. So, straight probe is at maximum electric intensity and the loop coupling should be at the position of maximum magnetic intensity if we want the desired mode to be excited in a particular rectangular cavity resonator. So, for that purpose we always have a graph of the movement of the electric and magnetic field. So, we should follow that one, and as per that we will have the straight wire and the coupling one. Now comes the turn of a circular cavity resonator. The same as we have in a rectangular cavity resonator, in the circular cavity resonator can also that is constructed from the circular waveguide with the z direction bounded from the one end and open at one end. In the case of a circular waveguide, the z is open at both the end, but in the case of if we want to design the resonator from that one, we have to close one end. A circular cavity resonator is a circular waveguide with two enclosed by a metal valve. The wave function in the circular, actually it is saying that the two enclosed, basically a small pore is just given at the one end is completely closed and a small pore is given at the one end for the excitation. That is why it is said, somewhere you will say that it is closed at one end and open at the one end, and somewhere it will be have both the two end closed because the small aperture is open at the one end for the excitation purpose and other end is completely closed. The wave function in the circular resonator to satisfy the Maxwell equation and the same boundary conditions as we have seen earlier. In that case, we are able to get the magnetic field equation Hz is equal to S0 Z Zn Jn within bracket x dash and p r a cos n phi sin q pi z upon d. Same in the circular, this is the open ended where the wave is propagating e to the power in the term of propagation constant, but here it is bounded, that is why it is a fixed one. N is equal to 0, 1, 2, 3 and it is the number of periodicity in the phi direction. P is the number of zeros of the field in the radial direction and Q is the number of half waves in the axial direction. The now the N and P is same as the we have studied for the circular, and Q is also the same one. Zn, Jn we know that is the Bessel function of the first kind, and S0 is the amplitude of the magnetic field intensity. And similarly, Ez equal to E naught Z Jn x Np Ra cos n phi cos q pi Z upon d. Here you are able to see that the expression of T and the Tm modes are different in many respects. So, the separation equation for the T and Tm modes are also different. And now, if the separation equation for the T and the Tm modes are different, of course, the resonant frequency which we get from this equation will be also different for both T and the Tm mode. So, substitution of that value in k square is equal to omega square mu epsilon is the resonant frequency for the T and the Tm mode different, and you will have these values for the T and the Tm modes of the circular resonator cavity. And in this case, in the case of a circular resonator cavity, the dominant mode is given by Tm110. Of course, this is opposite to that of the which we have in for the rectangular cavity resonator. For the rectangular cavity resonator, the dominant mode is the Te101, and for the this one, the dominant mode is Tm110 if 2A is greater than D. Condition in all the dominant mode calculation, the condition is applied. If this condition is not satisfied, this dominant mode will not exist, and T11 will be the dominant mode if D is greater than and equal to 2A. So, if the reverse happens, the dominant mode will change accordingly, and in that case the dominant mode is Te111. So, this question will comes to you in the 2 marks questions and the multiple choice questions in the university level also or in the competitive examination, because the waveguide, cavity, S parameters, these components of transmission line which we have studied earlier are very much important topics in various competitive examinations also. So, you should remember this, in what condition which dominant mode will exist. Now comes the semicircular cavity resonator. So, semicircular cavity resonator can be obtained by simply cutting the circular cavity resonator, and the dimensions we are having the same, but there is some changes. The wave function in that case for the T and PQ mode in the semicircular resonator cavity can be written as this one, Hz is equal to H naught Z Jn x dash Np A cos n phi sin q pi Z upon D. So, if you are able to see the expression of the previously obtained this function, is there a difference? There is not much difference over there here, and same thing, A is the radius of the semicircular cavity resonator, D is the length of the resonator, same as we have for the circular cavity resonator. N is equal to 0 to vary from 0 to and multiple numbers 0 to 1, 2, 3, 4, 5, 6 and so on. Q same as the circular cavity, and the values which exist for the circular cavity same for the semicircular. And for the wave function for the Tm and PQ mode, Ez equal to E naught Z Jn x Np R A sin n phi cos q pi Z upon D. Now, from the same expression, we will have the expression of the resonant frequency. The resonant frequency, if you are able to see, the resonant frequency is also same for the semicircular cavity resonator and for the circular cavity resonator. You can definitely verify it will be the same. Now, the dominant mode. Dominant mode, if you are able to see the dominant mode, what is saying here? The T11 for the D greater than A. So, simply T11 for D greater than equal to 2A. So, the expression is only the change in the 2. So, the only difference here is the 2, and similarly TM1110 if D is less than A, and in the case of a circular cavity resonator it is just 2A. So, this is the minute difference between the circular cavity resonator and the semicircular cavity resonator. Now comes the turn of a Q factor of a cavity resonator. The quality factor is a measure of the frequency selectivity of a resonator or anti-resonance circuit, and is defined as Q is equivalent to 2 pi maximum energy stored upon energy dissipated per cycle. So, this will be omega W, and this is equal energy dissipated per cycle is equal to P. So, if we remember the first slide, in that case basically in the cavity resonator case we comes the value of quality factor always. Whenever there is a cavity resonator, we always use a very important factor of that is quality factor. Maximum energy stored can be determined in the terms of inductance and capacitance, that is the energy stored in the cavity. Energy dissipated per cycle can be determined in the terms of resistance. So, we have that two expression. At resonant frequency, what is happening? The electric and magnetic fields energies are equal, and in time quadrature magnitude will be equal, but the phase will be different. When the electric field is maximum, electric field is 0, and the vice versa. The total energy stored in a resonator can be obtained by epsilon by 2 E squared dV per volume integration with respect to the complete volume. That this is the electric field energy, and the magnetic field energy mu upon 2 H square dV complete integration through the complete volume. E and H are the peak values of the electric field intensity, and now the average loss in a resonator can be evaluated by integrating the power density over the inner surface of the resonator, and that is equal to P is equal to Rs upon 2 integration surface integral Ht, that is tangential component of the magnetic field, its magnitude square integration with respect to area. And when we see Ht, which is our tangential peak value of the tangential magnetic field intensity, and Rs is the surface resistance of a resonator. And now what we are going to do? We have a quality factor omega W by P. So, we have calculated the value of energy stored. I am just writing it here. I have written it in the terms of magnetic field. We have obtained the energy stored both in the terms of electric field and the magnetic field. But in the expression which I have shown you for the Q, we have written this one because we have obtained the value of P, that is energy power dissipated in the terms of magnetic field. That is why we have taken this expression. Otherwise, you are free to take this expression also. Now, 2 from the both the denominator get cancelled, otherwise the same expression omega mu H square dV Rs surface integral Ht square dA. And now the main twist comes. Since the peak value of magnetic field related to the tangential component and the normal component, we know that complete H is equal to Ht square plus Hn square. Hn is the peak value in the normal magnetic intensity, and Ht is at the resonator wall is approximately twice the value of H square. So, what we are getting that Ht is twice the H square. So, we can replace with the 2 and both the get cancelled, 2 r as omega mu with respect to volume and with respect to surface area. So, this will be the our quality factor expression. So, being the twist is this one, twice the value of h square. And now, if we are taking a simple unloaded resonator, in that case our resonant frequency can be written as 1 upon 2 pi under root LC and the quality factor is given by omega naught L upon R. So, here comes the end of the resonate cavity of the microwave cavities. So, thank you for attending today's lecture.